Hi, I'm Kevin Zhou. I'm a particle phenomenology graduate student in SLAC, and today I'd like to tell you about some of our new ideas for detecting axion dark matter. In this talk, I'm going to be using a relatively expansive definition of axions. So for me, an axion is any light pseudoscalar field whose mass is protected by shift symmetry. These fields are theoretically well motivated in that they appear in many UV completions of the Standard Model, and cosmologically they have a simple and predictive dark matter production mechanism, namely the misalignment mechanism. Here I've shown the axion mass versus the Peccei-Quinn symmetry breaking scale Fa, and there's a wide range of parameter space allowed for these kinds of particles. However, there are a few especially interesting regions of parameter space I want to highlight. First, in yellow, I've shown the QCD axion, the original motivation for axions, which solves the strong CP problem. In blue, I've shown ALP-DM, and what I mean by this is that this is the set of parameters so that you automatically get the right abundance of dark matter, assuming only that you have an order 1 misalignment angle and a temperature-independent axion mass. Finally, the left end of this plot shows fuzzy DM, which has de Broglie wavelengths on the scale of dwarf galaxies and may help resolve puzzles in galactic scale structure. Most axion search experiments to date have used the generic electromagnetic coupling to photons. And the way this coupling works is that it acts as an effective current in the presence of a magnetic field, which is proportional to the magnetic field times the time derivative of the axion field. If one has a static magnetic field background, then this produces a small effective current oscillating at a frequency about 1 gigahertz for axion masses about 1 micro eV. The Schivy haloscope is a classic idea used to probe these kinds of axions, and the idea is to resonantly amplify this small oscillating current in a microwave cavity whose resonant frequency is tuned to that of the axion mass. And this has seen great success with ADMX, Haystack, and other experiments. However, we would also like to probe axions at lower masses, and in this case, the cavity approach breaks down because the cavity would need a huge size of order the constant wavelength of the axion. Therefore, any experiment that works in this regime has to decouple its resonant frequency from its size. In the past 10 years, two qualitatively new approaches have emerged. One is the LC circuit approach, which is exemplified in ZM radio and Abracadabra. And here we use a lumped element circuit, which allows the resonant frequency to be much lower than the inverse size. Another approach is Casper, which uses nuclear magnetic resonance. And in this case, the resonant frequency is set by the external magnetic field. However, Casper only, in this case, I've shown Casper, but it only probes the QCD axion because it directly probes the axion-gluon coupling. So it does not probe the rest of this parameter space shown. What we see here by combining these reaches is that there is still an interesting gap in coverage of the QCD axion in between Casper and TM radio. And in general, there's limited coverage of lighter axions for ALP-DM or fuzzy dark matter. Remarkably, this new heterodyne approach fills in precisely these gaps. And now I want to tell you why it does this. The first step of the heterodyne approach is, instead of using a static field, to load a cavity mode at a non-zero frequency, omega naught, which is on the order of gigahertz. Here I've shown it done with 2 loading ports connected to loading waveguides, which are driven by an internal oscillator, but the particular hardware can be achieved in many ways. Now, the axion effective current is always proportional to the magnetic field times the time derivative of the axion field. And since these two quantities oscillate at frequencies of omega naught and NA respectively, the effective current now oscillates at frequency omega 1 equal to their sum. Therefore, if there's also a cavity mode at that frequency, then we can resonantly drive power into that mode, which we call the signal mode. And this driving is efficient if the field of this mode is locally orthogonal to that of the loaded mode. Remarkably, the axion-induced signal here is parametrically larger than one would get in the corresponding static experiments. And this can be seen directly using Faraday's law. The EMFs we would read out due to the axion field are proportional to the time derivatives of the magnetic fields due to the axion. The magnetic field itself is proportional to the effective currents, which is the same in both cases, but the time derivative picks up a factor of MA if you're using a static field, and omega 1 if you're using this heterodyne approach. Therefore, we have a parametric advantage of omega 1 over MA, which gets stronger and stronger the lower the axion mass is. This is how you would probe the axion mass for a single value. If you want to scan over distinct axion masses, then you would need to perturb the cavity walls to shift the difference between the two mode frequencies. So one example method I've shown here is to add some rods that are moved in and out using some piezoelectric actuators. One qualitatively different feature is that because both these mode frequencies are always much larger than the axion mass, many orders of magnitude in the axion mass can be scanned by only small fractional changes in omega naught and omega 1, and therefore small displacements of the cavity. This distinguishes it from static field cavity experiments, which often need elaborate tuning mechanisms. An important noise source that we need to worry about in this approach is leakage noise. So I've just explained how energy fed in at frequency omega naught in the loaded mode can be converted to energy frequency omega 1 in the signal mode. In addition, environmental noise sources at the same frequency MA can also convert energy in the loaded mode at frequency omega naught, into energy at omega 1. And then if the signal mode has some coupling to the loaded mode, parameterized by a small cross-coupling epsilon, this will be read out as signal. This problem motivates the use of an SRF cavity because the power and leakage noise is proportional to the power we put into the cavity. Therefore, we want to have as low an intrinsic dissipation as possible. For our purposes, we consider quality factors up to 10 to the 12. The specific sources of external noise at frequency MA that we need to worry about for leakage noise are vibrations of the cavity wall and imperfections in the oscillator driving the cavity. For the oscillator, this happens simply because no oscillator is perfectly monochromatic, and it turns out that the dominant source of spectral spread for oscillators is phase noise, which are fluctuations of the phase of the oscillation. In addition, we also have some more typical noise sources for cavities. First is field emission, which is that if the electric fields on the surface of the cavity are too large, they'll rip electrons off, therefore dramatically increasing the dissipation. This in practice sets a limit on the magnetic field inside of about 0.2 Tesla. In addition, the signal mode also is thermally excited. In this case, it's impractical to use a dilution fridge because the cooling capacity would not be high enough. So we just assume that we have typical superconducting temperatures of 2 Kelvin, which can be achieved with a normal helium bath. In this slide, I show how these noise estimates work as a function of axion mass. So in the y-axis I probe, I've shown the total noise power that one would expect for a single scan step probing that axion mass. In blue, I show the result of mechanical vibrations, and the power here is suppressed by two small parameters. One is the cross-coupling epsilon, and the second is delta, which is the fractional wall displacement. The particular frequency dependence here depends on things like the spectrum of the external forces acting on the cavity, which we've inferred from existing experiments, and also the spectrum of the mechanical modes of the cavity itself, which have a cutoff at around kilohertz. In red, I've shown the effect of phase noise in the oscillator, and this is suppressed by three small quantities: the cross-coupling epsilon, the power spectral density of the phase noise, which we get from data sheets and commercially available oscillators, and the intrinsic quality factor. And finally, at the bottom, we have the usual thermal and quantum noise, which are relatively independent of the axion mass. These dominate for high axion masses. In order to estimate how important leakage noise is, we need to use experimental precedent. And luckily, there are experiments that have used related ideas. In 2005, the MAGO collaboration attempted to use a very similar idea to detect gravitational waves. And they used an active control system to suppress their leakage noise by a factor of 10 to the minus 7. Currently, the dark SRF experiment is attempting to use SRF cavities to detect dark photons using a light shining through wall setup. In order for this setup to work, the mode frequencies of the two SRF cavities have to be stabilized to be equal to each other. And they've achieved mode frequency stabilization of a factor of 10 to the minus 10, which corresponds to cavity wall displacements controlled at the same factor. In this slide, I showed the potential reach of our heterodyne approach. In particular, if you focus on the high mass regime, if the volumes are similar to that of a static field LC circuit experiment and the thermal noise is limiting, then the SNRs are compared in this way. So first, there's a parametric advantage of omega 1 over MA, which I discussed earlier, and then there's the dependence on the quality factor of the resonators, the temperature, and the magnetic field. Our quality factor can be much higher because we're using an SRF cavity. The temperature, unfortunately, is also much higher because we have dissipation, which prevents the use of a dilution fridge, and B is much lower because of the field emission cutoff. It turns out that if you plug in the numbers for these three factors, they roughly cancel out, leaving only the parametric advantage of omega 1 over MA, which explains why we're able to probe the QCD axion at a lower mass range. In addition, this parametric advantage allows our sensitivity to survive as the axion mass goes to 0, therefore giving us a very wide range of reach for alpha dark matter and fuzzy dark matter. In addition, what we managed to show recently is that most of this parameter space, especially for lower MA, can be covered broadband without the need to set up a scan. And what I mean by broadband is that you can have two degenerate cavity modes, so just omega not equal to omega 1, and then look for axion transitions between the loaded mode and signal mode off resonance. This can be probed a wide range of parameter space very quickly without the need to instrument the scan. In the next two slides, I show how this reach changes with respect to degradations of the parameters. So here, I degrade the quality factor by a few orders of magnitude. Quality factors of 10 to the 10 are typical in mass-produced SRF cavities, and these increase both the leakage noise and the thermal noise. However, a substantial reach survives. We aim for a quality factor of 10 to the 12, and existing SRF cavities have already achieved factors of 2 times 10 to the 11. Here, I show the effect of increasing the amount of leakage noise parameterized by epsilon. And in particular, if one increases epsilon by 2 orders of magnitude, which corresponds to increasing leakage noise by 4 orders of magnitude, the reach at high axion masses is almost unchanged because thermal noise continues to dominate in this regime. In summary, the heterodyne approach has some crucial qualitatively new features compared to existing approaches. Compared to an LC circuit approach, we have a parametrically higher signal power, which becomes especially important at lower MA. Versus static field cavity, a single cavity using the heterodyne approach can scan over many orders of magnitude in MA using relatively small displacements of the walls. However, like both approaches, at high axion masses, thermal noise dominates, and this allows the reach to be estimated relatively straightforwardly. If this reach can be realized, then there's a wide range of physics potential, including probing the QCD axion in a heretofore unexplored region, probing the entire viable mass range of fuzzy dark matter, and 10 orders of magnitude in axion mass for ALP dark matter. At SLAC, we were beginning a small-scale prototyping effort to investigate leakage noise in a room temperature cavity, but it kind of fell by the wayside in March 2020 and has not been picked up since. But once the apocalypse ends, there will be a multifaceted experimental program required to realize the potential here. In particular, the design of the cavity is quite non-trivial because there are competing constraints. We want to have simultaneously a high magnetic field without field emission in order to increase the signal power, a high quality factor to decrease the noise, and also a wide scan range. In addition, we would need to implement active feedback systems for epsilon, as in the MAGO experiment, and delta, as in the dark SRF experiment. And finally, like DM radio, we would like to maximize the scan speed using overcoupled quantum limited readouts. If these obstacles can be overcome, then we believe that the potential of this approach is very promising. Thank you.